Welcome to Section 8-3, Changes in State. Just so you know, I always forget this, but we skip over Section 8-2. It's not something I teach you about. So we're going to talk about changes in state, but first thing I want to point out is that the word state sometimes gets replaced with this word, phase, on the state test. So I always worry that I should bother to teach you that term. So you should know that phase and state mean the same exact thing. So this is a picture showing you water going through the different states, not including turning to a plasma. So we start out, we're solid water, we're a crystalline solid right here. And the first state change is called melting. It takes 335 kilojoules of energy to make 1 kilogram of water melt. It's a lot of energy. The reverse process, going back from a liquid to a solid, is called freezing. These are things you already knew. If you're going to freeze water, you have to release that much energy. So you'd have to release 335 kilojoules of energy from your kilogram of water, and it would have to go somewhere, and it would go into the surroundings. This is an interesting point that the chapter brings out about state changes. When something changes state, it's exchanging energy with its environment. So when solid water melts, that means that we're taking energy from the environment and putting it into the water in order to make it melt. But if some bit of water is condensing, let's say it's going to freeze onto your windshield, right? Let's say there's liquid water that lands on your windshield and then freezes because it's really, really cold on that glass. If that happens, then that water has to release energy in order for those molecules to slow down and freeze. Where's that energy going to go? It's going to go into the surrounding air. And this is an interesting little fact that few people realize. When it starts to snow, that's rain turning into ice. And when that ice forms, the surrounding air warms up a little bit. So it always gets a degree or two warmer every time it snows, which is why it's really hard to get snow when it's right at the freezing point. So if it's exactly 30 degrees Fahrenheit, it's very unlikely you're actually going to get any snow to stick, because as it forms, it'll just melt again because the surrounding air has been warmed up. Very annoying. Now, liquid water requires a lot of energy to turn it into a gas. And there's two ways you can turn to a gas. Both are called vaporizing. You can see that here. And vaporizing comes in two forms. If you turn to a gas below the boiling point, that's called evaporating. Evaporation can only happen at the surface of a liquid, which is why it's so slow and takes such a long time for something to evaporate usually, unless there's a very tiny amount of it. So like a puddle will slowly evaporate over a number of days. You'll never see the water boiling, but each layer of the top surface of that puddle is peeled away one strip at a time and turned to a gas. Boiling, by contrast, does happen at the boiling temperature, and it happens throughout the entire liquid, which is why you start to see bubbles, because if a particle of water turns to a gas in the middle of a glass of water, that is going to form a bubble and it's going to go flying up to the surface. And that's why things that are boiling have bubbles in them. So your liquid vaporizes and turns to what we call vapor. And I think I pointed this out in class. You cannot actually see gaseous water, but you will often see condensed clouds of water around gaseous water. We call that steam. So water vapor, however, is invisible because the particles are really, really far apart. There's two state changes on this diagram that get mentioned in the packet that you probably don't realize that you see because they happen pretty rarely. One is called sublimation, and that's when a solid turns directly to a gas without passing through the liquid phase. Water can do this, and it does it all the time in your freezer, but you don't tend to notice it, because who notices when something's turning to a gas in tiny, tiny amounts? You can also take gaseous water right out of the atmosphere and have it condense onto a surface as a solid, and this is how you get frost when it hasn't snowed or rained. You might walk out on a cold winter day, or usually in the fall you'll notice this. You'll come outside and the grass is covered in sort of a skim of ice that we call frost. That came directly from the air. Gaseous particles of water in the air touched down on that cold, cold ground and froze instantly. It happens on your windshield sometimes too. On a really cold day, you'll get up, you'll go outside, and it won't have snowed, but there'll be a layer of ice on your windshield. That's called deposition. So the chapter brings up all these different state changes, and it talks about the amount of energy that's needed to go from one state to another. So two things come up, and they're right here. One is called the heat of fusion, which is the amount of energy it takes to melt something. That's the heat of fusion. And it's different for every substance because every substance has a different amount of attraction between its particles. They're different types of magnets. And the other one is called heat of vaporization. For water, these are the amounts, but it's different for every substance. Water is notoriously difficult to make it change from a liquid to a gas. And because of that, water makes a really good heat sink. It can absorb lots and lots of heat energy before it starts to evaporate or boil away. The other thing that comes up in this section is the heating curve for water. This is called the heating curve, what you're looking at here. And we've made a couple of them now, and we collected some data so you could see that whenever you heat something, and it goes through a state change, you're going to get what are called plateaus or flat parts on a graph. And these flat points are where the state change is happening, at what temperature. For water, on the Celsius scale, water freezes and melts at 0 degrees Celsius. Believe it or not, melting and freezing are the same process. If you think about it, melting and freezing are a condition of the molecules of a substance where they're sort of between the liquid arrangement and the solid arrangement. And if you're at exactly 0 degrees Celsius, those particles have exactly the amount of energy they need to start to slip between those two things. But whether or not they continue to melt or they go ahead and freeze is going to depend on whether or not the temperature goes up or down. If the temperature stays right at 0 degrees, what you'll get with a time-lapse picture of, say, an ice cube that's being kept at exactly 0 degrees Celsius, what you'll get is an ice cube that keeps changing shape very, very slowly as it melts and refreezes, melts and refreezes, melts and refreezes. So melting and freezing both occur at 0 degrees Celsius. A lot of students have the misconception that melting has to happen at a higher temperature than freezing, and that's just not true. The same thing is true for boiling. Boiling and condensing are the same process in reverse, and so they both happen at 100 degrees Celsius for water. You get these plateaus because during the state change, the molecules are changing their position, which doesn't allow them to speed up or slow down. So instead of changing how quickly they're moving, instead of converting the energy that we're giving them into kinetic energy, they're converting it into potential energy. They're using it to change their location relative to one another. So there's a series of diagrams in the book that you've looked at. You've made your own heating curve, and the cooling curve happens the same way, but in reverse. So if I were to draw a cooling curve for water on this same diagram, let me do it in, let's see what would be a good color. Let's do purple. So this is what would happen. You'd have your gas cool down, molecules are slowing down, then they would be stuck at a plateau while all of that gas turned to a liquid. And then the temperature would drop again, and when it got to 0, it would plateau as the substance began to turn to a solid. Once every particle had turned to a solid, you'd get a drop in temperature again as the substance continued to cool off to whatever the temperature of the environment is. So that's the reverse of the heating curve. Notice that the melting and freezing points happen at the same point, right? This is your freezing temperature, and this is your condensing temperature. And that is chapter 8, section 3, and hopefully I will see you in 8-4.